Welcome back, everybody. This is part 2 of chapter 7. In the previous section, we were estimating a proportion using a confidence interval. This time we are estimating a population mean. Now there's two ways that we are going to be doing this. The first one is going to be if sigma is not known. Now sigma, again, is the population standard deviation. And if that's not known, then we can't use a z distribution like we have been. We have to use a t distribution. And it looks like this. T equals x bar minus mu over s divided by root n. And yeah, so there's our new t distribution. Now, the nice thing is it looks a lot like z distribution as far as especially as n gets really large, then it looks almost exactly the same as far as a bell shape curve. A t distribution for all sample of size n. Now with the t distribution, each of the curves that we get depends on what n is. So we have to find our critical values, so t sub alpha over 2. To find our t critical values, we require what's called degrees of freedom. And often I'll just write df. But the degrees of freedom are n minus 1. And we used to need a table to do this. Some of your calculators are not going to have the button that I'm about to show you on the calculator, and so you'll need to download a t distribution table. You can go to the internet and literally type in t distribution table, and thousands of them will come up. You can print any of those out on your screen. That's fine too. So let's do this. Example 6, a sample size of 12 is a simple random sample selected from a normally distributed population. Find the critical value t sub alpha over 2 corresponding to a 95% confidence level. So in this case, our alpha is 0.05, which means alpha over 2 is 0.025. Now to find t sub alpha over 2, we need to recognize that n in this case is 12, which means our degrees of freedom is 1 less than that, 11. And I'm going to show you how to do this on a calculator. We're going to use something called inverse t. Now, we've used inverse norm, so it's kind of the same idea. Here's the thing. Some of the older models of this type of calculator do not have that function. I've written a program that if I'm teaching live with you, I can give to you. But otherwise, we're going to have to use a table. So I'm going to go ahead and use the button because many of them are going to have that. Again, this is going to be area to the left, just like with the other. So this is going to be 1 minus 0.025. And you'll notice it asks for the degrees of freedom, 11 in this case. This one takes a second, I think. There we go. So this gives us t sub 0.025 in this case is about 2.2020. Now let's go to 3 spaces. So we'll go to there. Now I want to show you how to do this on a table as well. So we are degrees of freedom at 11, and we are going to be here. There we are. 2.201, which is exactly here. 2.20, and then they round it off to 1, just like we did actually. So it's not hard to use the table. You just need to know what you're looking for. By the way, one tail has 0.025 in it, and if it was 2 tail, it would have a total of 0.05, which was my alpha. So not too bad. To construct a confidence interval used to estimate the proportion mean without sigma known, this is the big deal. This means t distribution. If it was known, we would use a z distribution, then we would use inverse norm, which all of your calculators will have. The requirements are that the sample is a simple random sample, and the population is either normally distributed or n has to be bigger than or equal to 30. All right, so our confidence interval is going to look like this: x bar minus e, x bar plus e, where e is t sub alpha over 2 times s divided by root n. The freedom n minus 1. All right, important properties of the t distribution. The t distribution is different. Different for different sample sizes. That's because it depends on the degrees of freedom. The t distribution has the same general symmetric bell shape as the standard normal distribution. So that's what I mentioned up here. A t distribution has a mean of 0. Well, this were our distribution, the mean would be 0. The standard deviation of a t distribution varies with the sample size, but it is greater than 0, so it's always positive. And I mentioned this before as well. As the sample size n gets larger, the t distribution gets closer and closer to a standard normal distribution, a z distribution. All right, here we go. Example 7. A sample of 106 body temperatures have a mean of 98 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. Construct a 95% confidence interval estimate of a mean body temperature for the entire population. What does this result suggest about the common belief that 98.6 degrees Fahrenheit is a mean body temperature? Okay, so we could go through and crank all this out. However, what we're going to do instead is learn how to do it with our calculator. So we're going to go to stat. We're going to go to tests. And we're going to scroll down to a t interval. And we're not going to use data. We're going to use our statistics. So let's write down what we do have. So we have x bar 8.2. We have our standard deviation of 0.62. And we have n equals 106. Now, those of you that would need to look this up on a table, you'll notice we don't have a 106. You would have to use the 100. And we have our sea level is 95%. Now, we are using, change colors here real quick. This is called a t interval. And here we go, t interval. Again, you get here by going stat, tests, and then t interval. All right, so x bar, 98.2. Standard deviation, 0.62. N is 106. Our sea level is 95%. And ladies and gentlemen, we're done. So our t confidence interval is 98.081 with mu in the middle, and then we have 98.319. These, of course, are degrees Fahrenheit. Degrees Fahrenheit. So we are 95% confident that the true mean is between 98.081 and 98.319. Now, let's answer the second question. What does the result suggest about the common belief that 98.6 degrees Fahrenheit is a mean body temperature? So we're 95% sure that the true mean body temperature of all human beings is not 98.6 degrees. It's lower than that. So for the second part, mu is probably not 98.6 degrees Fahrenheit. Interesting. Moving on to the next page. All right, so we have our next example. Listed below are the speeds in miles per hour measured from southbound traffic. The speed limit for this road is 65 miles per hour. Use the sample data to construct a 95% confidence interval for the mean speed. What does the confidence interval suggest about the speed limit? All right, so I have already inputted this into list 1. You may need to pause this video so that you can put yours into a list. It doesn't matter which list. But once you get it there, once again, we're going to be using T interval. So I'm going to quit out of this, quit. And to get there, I go to stats, tests, and down to T interval. Now I am going to use the data because I have my data in list 1. If you remember how to change that from mine's L3 to L1, L1 is above the 1, so I got to hit second and L1, and it changes it to L1 for me. There's no frequency. The sea level is 0.95. And we're done. You got to love the technology. It's absolutely amazing. So there's my confidence interval. Now, as we look at this, it says, the second part says, what does the confidence interval suggest about the speed limit? Well, the speed limit, they say, is 65 miles an hour. Speed limit's not in here. Now, we can see there are some people that exceeded the speed limit. Not very many, actually, in fact, just the one, it looks like. So what does this tell us? That 65 miles per hour is probably not the mean. I'm using the word probably. That's an everyday word that you and I use all the time. I'm using it in a statistical form, meaning the probabilities that this is in here is very, very low. Now, what if we have a Z distribution? In this case, this means that sigma is known. So we have a few things that we need to, a few requirements. The sample has to be a simple random sample, and the population is normally distributed, or just like the other one, n has to be bigger than or equal to 30. All right, and our confidence interval is going to look something like this. X bar minus E, mu in the middle, X bar plus E, or E. It's going to look very similar to the T distribution. Is Z sub alpha over 2 times, now this has to be known, right? Otherwise we can't use it, over the square root of n. And you'll notice there's no degrees of freedom with this. It's not necessary in this case. So example 8, it says the number of chocolate chips in a sample of 40 cookies has that the mean is 23.95 chocolate chips. Construct a 99% confidence interval, assuming sigma is known to be, so that they literally tell us that sigma is known to be 2.55 chocolate chips. All right, good news. We also have a Z interval. once again, let's put this up here. I'm going to go to stat test, and you can see z interval here is 7th on mine. And in this case, we are not going to use data. We're going to use the information they give us. And the first thing you want to know is, what is sigma? Well, that is 2.55. X bar, 23.95. N is 40. Confidence level is 0.99. Just like that. You gotta love it. I'm going to double check my numbers. .55. The mean. Oops, that is not the mean. Oh, I mixed it up. 23.95. Better. All right. So confidence interval is 22.911. 24.98 enough. Pretty easy stuff with the technology. Now we're going to be finding the sample size. All right. We have a formula. Let me switch color. N equals Z sub alpha over 2 times sigma over E. And all of that is squared. And again, this is the minimum sample size that we can have to guarantee a certain level. Let's move that up so we can see everything. So for this one, a little low on space here. So alpha in this case is 0.1. Alpha over 2 is 0.05. And I'm going to use inverse norm to get my z sub alpha over 2. So just inverse norm, because we a z distribution, which we've used before. So this is 1 minus 0.05. There we go. So z sub alpha over 5 is about 1.64. Once again, I'm going to store that off using memories. Store. Okay. Here we go. So let's also make it clear. We have the standard deviation, 15 in this case. E in this case is 3. So sigma in this case is 15. E in this case is 3. All right, here we go. N equals 1.64 times 15 divided by 3 squared. Here we go. So I'm going to use A instead of the 1.64 times 15 divided by 3 and then squared. There it is. So what's the minimum we would need? These are adults again. So this is about 67.639. And once again, we always round up. 68 adults. Confidence intervals of a mean. Good stuff.